Hey, here we go, rational functions. I've got wonderful news for you. If you loved polynomial functions, you're going to love these even more because rational functions are just two polynomial functions stitched together by division. If you flip to the second page of our notes today, you can see a couple rational functions that we're going to be tackling at the end of our notes. And it just consists of a polynomial divided by a polynomial. So a lot of the work that we've already done with polynomials is going to be useful to us. What's going to be different about these things as opposed to polynomials? The main difference is going to be the rational functions. We're going to have to worry about asymptotes. So we'll see some vertical asymptotes, which you guys have heard of before. But we're also going to be talking about end behavior asymptotes. That'll be a big difference from last year. Last year, you were taught a lot about horizontal asymptotes. We're not going to call them horizontal asymptotes anymore. We're going to call them end behavior asymptotes. And the reason is they're not always horizontal. So last year, they simplified things for you a little bit, only through rational functions at you that had horizontal asymptotes. This year, we're going to see some end behavior asymptotes that are slanted. We call those oblique asymptotes. We'll even see some that are quadratics and cubics. Okay, so they're not all going to be lines, and they're definitely not all going to be horizontal lines. Before we get into all that, though, I want us getting familiar just with the concept of a vertical asymptote, and then also being able to talk about the behavior of the graph around the asymptote. So first of all, when we're looking at a graph of a rational function, when we see vertical asymptotes in particular, I want you focusing on, when you look at this graph, I want you seeing two vertical asymptotes. A lot of times my students, when they start with rational functions, they look at a graph and they see there's 1, 2, 3 pieces to this graph. Don't look at it like that. There's not 3 pieces to the graph. This is one graph. It happens to have two vertical asymptotes. Okay, when we look at the vertical asymptotes, I need you to be able to just look and focus your attention just on the area to the left and to the right of the asymptote. So sometimes my students will find it helpful to have a couple pieces of paper and they'll sort of block off the function so they're just looking at what's happening on the left and the right of the asymptote. Okay. So I want you to think about this asymptote here it's like a little guy and he's got 2 arms. Okay, we're gonna learn some dance moves in a minute here with these 2 little arms. So right now, this guy's got 2 little arms. He's got an arm on the left. Which way is his left arm pointing? It's pointing down. And which way is his arm on the right pointing? It's pointing up. So if I were to ask you about the behavior of this graph around the asymptote, you would say to the left of the asymptote, the graph is going down, and to the right of the asymptote, the graph is going up. Can you guys see that? When we kind of isolate it? Well, here's how we say this in limit notation. So I want you to first focus on this arm here that's pointing down. So this says the limit as x approaches -2, and then there's a little exponent here with a negative in it. There's no number, it's just a negative. We read this as the limit as x approaches -2 from the left. Notice that this asymptote here is at x equals -2. So what this is saying that as the graph comes into that asymptote from the left, the y value goes down to -infinity. That's saying that that left arm of this asymptote is going down. If I want to talk about the right arm instead, I write the same thing except the little minus turns into a plus. I would read this as the limit as x approaches -2 from the right of f of x is what? What's my right arm doing for this asymptote? It's going up, so we would have positive infinity here. So this is slightly different from that end behavior limit notation that we used before, because we're going to be talking about not x going to -infinity or positive infinity, but we'll be talking about it going to a specific number from the left and from the right. So could you guys focus your attention on this other asymptote? Note that this one is at x equals +3. And could you please write me some limit notation for this? I'm going to get mine set up with just the stuff that's always in these, and then come back and fill in the details in a moment. So look at what those two arms are doing to the left and to the right of that asymptote. And see if you can fill in the details for our limit notation. Try and do that on your own. You've got pencils. If you make a mistake, that's okay. We'll erase and fix it. By the way, I made like 18 mistakes first period today going over these same notes. So would you guys please watch me and help me if I say something and write something else down, or if I just write the wrong thing down. What did I do earlier today? I said like 4 times 1 is 5. That's embarrassing. All right, how we do? The limit as x approaches 3 from the left. That left arm's going up. Did you guys put in a positive infinity here? Actually, both arms are going up, so you got a positive infinity for both of them, right? And this one looks exactly the same, but if we want to say if we're approaching 3 from the right, this will be a little plus here. That's also positive infinity. All right, so we introduced this limit notation back in chapter 1 to kind of get you guys used to it. We're just adding a little bit of a difference on here. Instead of a positive or negative infinity, we've got a number. Are we feeling okay about that? All right, I want you guys to practice your behavior, describing behavior. This is exactly copied word for word from the instructions in your assignment. So it says use limit notation to describe the end behavior and the behavior around the values not in the domain. Values not in the domain, they're talking about vertical asymptotes here. So go ahead and practice. You guys already know how to do end behavior limit notation. So give me 2 statements in limit notation format for end behavior. And then focus your attention on this asymptote and describe the left side and the right side for that. And then focus your attention on this asymptote, describe the left side and the right side for that. So you should end up with 6 statements altogether. I'm going to do mine up here, but don't just watch the screen and copy my answers. You guys know how to do this. Look up here if you need a hint. All right, so tell me about the left end behavior. Are we going up, down, or settling out to or leveling off to a value? This is leveling off to a value. So it's leveling off to, looks like it's going to level off around x equals 1. So we've got 1 here. And actually on the right-hand side, it's leveling off to that x equals 1 also. Sorry, y equals 1. Y equals 1. That's that horizontal asymptote. We're no longer going to call those horizontal asymptotes, though. We're going to refer to them as end behavior asymptotes, because they're not always horizontal anymore. Okay, behavior around the vertical asymptotes. Heading towards -5 from the left-hand side, looks like we're going up. Did you guys do a positive infinity for that one? And then heading towards that same asymptote from the right-hand side, looks like we're going down, so we want a negative infinity there. My other asymptote was at 4, so I'm heading towards 4 from the left. Looks like I'm going down here, so negative infinity. And heading towards 4 from the right, we're swinging up towards positive infinity. How are we feeling about describing behavior around asymptotes? It's that same kind of notation. You guys have sort of gotten used to it. Hopefully it's not looking too crazy to you at this point. When we describe behavior around asymptotes, it's either going to be going down to negative infinity or up towards negative infinity. We don't have the option of leveling off towards a value for a vertical asymptote. All right, let's move on and talk about some rational functions. So this is just a very general thing about vertical asymptotes. We're starting in on rational functions now. And the first thing we'll do with these, first thing we'll do with pretty much every type of function we'll deal with this year is we're going to graph them. And we're going to graph using transformations. So I want you to look at this first example and tell me if I were going to start at the graph y equals 1 over x, that would be my parent function for this. Can you look at this and tell me what's going on in terms of transformations? I'm open to see people shaking their heads no. Maybe a little bit. Is there anything in here that you would take a guess at? Like, what do you see happening? What would I do to 1 over x? Left 2, I agree. That's pretty much the only thing that I can see looking at this is left 2. But all this stuff up here, I don't expect to see that. It's supposed to be a 1 up here, and we got all this other stuff up here. Bless you. So how are we going to deal with that? Well, the key to it is if it's not in a nice, friendly format like this, if we could get it into a format that looked like this, then we would be able to say, oh, yeah, we got a vertical stretch. If that's negative, maybe we're reflecting. Be able to see shift left or right and a shift up or down. If I could make it look like this, then I would be able to talk about transformations, but this is not useful to me. So how are we going to get there? We're going to divide. So the key idea here is use division to make this look like this. All right, so we're going to actually divide this. We have two options. We could do long division or we could do synthetic division. Since this is first degree on the bottom, we could use synthetic division. Do you want to go with synthetic or do you want to go long? Synthetic it is. Let's do it. So I'm dividing by x plus 2, so I'll put my negative 2 in my box here. And I only have a couple coefficients, so this should go pretty quick for us. Negative 3 and negative 7. Negative 3, that's 6, that's negative 1. What was the point of doing that? Now that's going to allow us to write another version of this function's equation. It is negative 3 plus, and then we remember we always have our remainder goes on the top. And what would go on the bottom here? X plus 2, the thing we're dividing by. I am going to rewrite this one more time. Just rearrange things a little bit to make it look a little bit more friendly. There we go. That's nicer, isn't it? So I just pulled the negative from the top. I just pulled it out in front. And I put the minus 3 at the end. So now can you look at this and start talking about transformations? How many are you seeing here? If we were to start at 1 over x, how many transformations am I going to need to do here? I'm seeing 3 also, yeah. I see a reflection over the y-axis, shift left by 2, which we kind of predicted a moment ago, and then a shift down by 3. Cool. So let's do it. Actually, let's graph our parent function first. I need you to know what 1 over x looks like. It goes through the points 1, 1, and negative 1, negative 1. And it has 2 asymptotes, a vertical asymptote at x equals 0 and a horizontal asymptote at y equals 0. Looks like that. So we're going to graph our final graph the way we've been graphing by transformations. We're going to make some little tables, track some x and y coordinates. The nice thing is we only need to track 2 points, but we also need to track these asymptotes. So let's start with our equation. Our parent equation was y equals 1 over x. And I'm going to do an xy table. And I'm also going to track my asymptotes, x equals 0 and y equals 0. Which of our 3 transformations should we do first? We got a reflection and a couple shifts. What should we do first? Reflection, you want to save the shifts for last? That's usually the easiest way to go. So yeah, let's do the reflection over the x-axis first. That's just going to put that negative out in front. What's going to be modified when we reflect over the x-axis? The x values or the y values? The y values get affected because it's a vertical thing. It's outside the function. So these y values are going to change, and our y equals equation is going to change, or potentially could change. Everything else remains the same. So my x values I'm just going to copy over because they don't change at all. My y values, we just needed to multiply all those numbers by -1. So -1 times -1 becomes +1. 1 times -1 becomes -1. 0 times -1, actually I lied. That one doesn't change. It could potentially have changed. All right, that gets us to there. We've got a reflection taken care of. We just need to do our 2 shifts. You guys want some more good news? I'm okay when you're doing these if all you have are 2 shifts left to do. You can do them in 1 step if you feel confident doing that. So I'm going to go ahead and do it in 1 step here. Now, if this is too big of a bite for you, if you'd feel more confident doing them separately, you're more than welcome to do that. But I'm okay with you doing your shifting together. So we did a shift to the left by 2 and down by 3. So left by 2, that's going to affect our x coordinates. We're just going to subtract 2 from each of our x coordinates. So -1 minus 2 would be -3, and 1 minus 2 is -1. And then we also need to change this asymptote was at x equals 0. Since that's an x value, we need to subtract 2 from that also. Downshifting by 3, that's going to affect my y coordinates and my y value on my asymptotes. So I'm subtracting 3 from everything. So -2, -4, -3. That should give us enough to draw a couple points and a couple asymptotes, and that will be enough for us to make a pretty decent sketch of what this graph's going to look like. All right, so that should mostly be some review, except for this idea that we had to do some division to help change the format of our function into something that was easier to see our transformations. Do you guys have any questions about that? I have some questions before you turn the page. Last year you were used to calling this a horizontal asymptote, and it is. But the importance of this is that it's an end behavior asymptote. It happens to be horizontal, but the important thing about this is it's an end behavior asymptote. And I need you to understand what an end behavior asymptote tells us about the graph. So here's my question to you. Okay, and big hint, it has something to do with this end behavior asymptote. If I took my original function, or in either of these forms were the exact same thing, if I took my original function and I plugged the number 10,000 in for x, approximate for me what the y value I would get out of that function would be. If I plug 10,000 in for x, about what would you expect to see for a y value for this function without using your calculator? What are we guessing? Don't be trying to do any mental math because you don't even need to look at the function. The graph will tell you everything you need to know. If I plug 10,000 in, what am I expecting my y value to be? About, yes? It's going to be really close to -2. It's going to be really close to -2. The further out to the right I go on this graph, the closer and closer the y value gets to -2. That's what that end behavior asymptote tells me. I'm sorry, question? If I plug 10,000 in for x, which means we're going way off that way, way off of that way. Oh, I'm sorry. I drew this wrong. Yes, it would be -3. Is that what you meant? Did you mean -3? You said it and I said it wrong. Oh, there's my first mistake. Awesome. We'll see if I can get in under 12 today. -3 is the correct answer. Yes, it would be -3. I don't know why I was looking at this and I didn't do a good job drawing it. It would be -3. Yes, yes. Okay, what if I put -10,000 in for x? What would you expect I would get for my y value? Not exactly, but really, really close to -3. Okay, that's what the end behavior asymptote tells me. It tells me if I go to extreme left and extreme right, if I zoom out on this graph, what is the graph going to look like? And the graph is going to resemble, if you zoom out and you forget about everything in the middle, it's going to look like a horizontal line, y equals -3. Okay, that's going to come up today. We're going to be dealing a lot with end behavior asymptotes today. So let's start doing that. Here we go. This is rational functions on boiled down to like a half a page worth of notes. So what do we need to know? So we're going to be analyzing these rational functions. I'm going to give you an equation. We're going to be graphing it by hand. In order to graph it, we're going to need several features. We need to know x-intercepts. Those are super helpful when we're graphing. It turns out that the x-intercepts are still the zeros of the function, which are going to be the zeros of the numerators. So the top of the fraction gives you your x-intercepts. The top of your fraction gives you the x-intercepts. And just like with polynomials, if one of those factors is squared, or to the 4th power or 6th power, then you're going to bounce off of the x-axis. But if it's a single factor to the 3rd or to the 5th power, then you're going to cross the x-axis. So that all works just like we're used to. It turns out that the denominator, the bottom of the fraction, is going to give us our vertical asymptotes. And there's something that we can predict about the way these vertical asymptotes look based on the multiplicity. But it's not bounce and cross, because we never cross a vertical asymptote. What it's going to be instead is it's going to tell us what that behavior on both sides looks like. And this is our second pre-calc dance of the year. So you guys ready? We're all going to participate. We'll all look goofy together. This is the way nobody's embarrassed, or everybody's embarrassed, whatever. Okay, so the graph's coming towards an asymptote. It's coming flat in towards the asymptote on both sides, okay? If it's an odd degree, an odd multiplicity, as it comes in, the two arms are going to go opposite directions. All right. Sometimes they'll go left on the, or up on the left and down on the right, and sometimes they'll go the other way, but they're always going to go opposite directions. Okay. Now, if it's an even multiplicity, as they come in, they're both going to veer off in the same direction. Either they'll both go up or they'll both go down. So odd multiplicity, they're going to dance like this. Even multiplicity, they're going to dance like this. We got it? All right. So just imagine your little asymptote guys with the arms doing their little dance. Okay. We'll come back to that in a minute. All right, the next thing we have to talk about is something that you are familiar with, but we're giving it a different name. Last year you talked a lot about horizontal asymptotes, and those are really useful to help us make our graph, but we're no longer going to revert to them as horizontal asymptotes. I don't need you to write down any place on your paper HA y equals 3. First of all, you don't need to write HA because when you write y equals 3, I'm going to know it's a horizontal line. Secondly, it's not always going to be horizontal. Okay? So there is a way to find end behavior asymptotes that works in every single situation that you're ever going to encounter for rational functions. And it's this third one, and this is probably going to be the new one. But this is the Swiss Army knife of dealing with end behavior asymptotes. Please make yourself a note that this always works. These other two boxes are hopefully look kind of familiar to you from last year. This is probably what they taught you in Algebra 2. That your horizontal asymptote depends on your degree of the top and the bottom of the fraction. Does that sound familiar? If it's bottom heavy, if it's bigger on the bottom, then it's automatically y equals 0. And if it's balanced, if you have the same degree on the top and bottom, then you take your lead coefficients and you divide them. These are shortcuts that only work in these two particular situations. However, you can deal with both of these situations using this third one. Okay, this third one always works. These ones only work if you match it up to the correct situation. So if you're ever on a test and you can't remember, ooh, is this the one where it's automatically y equals 0? Or is this the one where I have to divide? If you can't remember, then go with this, because this always works. Okay. So when you're looking at these situations, if you have a denominator with a higher degree, so I sometimes like to call these bottom heavy. An example, I didn't put an example on here, but this would be like if I had f of x equals, say it was like 5x to the 4th plus something, and on the bottom you had a 2x to the 5th plus something. It's bottom heavy. There's a higher degree on the bottom. Anytime that happens, you're going to have an end behavior asymptote of y equals 0. You don't have to do any work for it. You just have to recognize, oh, that's that special situation. We're going to have y equals 0. The coefficients don't matter. It's the degree that makes a difference, okay? The next one I call balanced. And balanced would be if I have the same degree in the numerator and the denominator. And in that case, then, the end behavior asymptote is just y equals, and then you look at the lead coefficients of both of your lead terms. So just divide them. Okay, so if this had been 5 and 2, then it would be y equals 2.5. All right, and then this one works all the time, but it's basically when these don't work. So this would be like a top-heavy equation. And we're going to jump down. We're going to skip past holes for today. Could you please make a note that we need to come back to this? I have a feeling we'll probably do it on Wednesday. I think we're going to run out of time today. And then we'll also come back to this. If we don't hit that today, please don't let me forget on Wednesday. All right, so let's look at an example. We've got a nice function here, and they just want us to find the end behavior asymptote. So look at this situation and tell me, is it bottom heavy? Is the degree higher on the bottom? No. Is it balanced? Is the degree same top and bottom? No. So can we use either of these two fun shortcuts? No. All right, but that's okay because we can always use this. And the key to this is we've got to divide. We have to divide. So we're going to do a division problem with this. Now that is a linear denominator, so we could do synthetic division. Would you guys like to do synthetic division? Yeah, let's go ahead and do synthetic division. So this would be a positive 1 inside my box. 1x to the third, 3x to the second, negative 4x, and negative 12. Am I going to be upset if I get a 0, or if I don't get a 0 for a remainder here? No, I've got no reason to think that this is going to divide out without a remainder. They didn't tell us x minus 1 is a factor. So I'm not expecting a remainder of 0. I won't be too upset if that doesn't happen. All right. So would you feel confident now writing a different version of this function's equation? What would that new version be? There's no constant. This is x squared. So it would be 1x squared plus 4x plus 0. I'm not going to write that part. Plus negative 12 over x minus 1. So then what's my end behavior asymptote? It's just y equals that. That's my end behavior asymptote. Do you see why we don't call them horizontal asymptotes anymore? Is that going to be a horizontal line? What's this graph going to look like? It's going to be a parabola. Our graph is going to resemble a parabola as we go out to the left and to the right. It's going to be doing some weird stuff in the middle. It's going to have some vertical asymptotes and some x-intercepts and stuff in the middle. But as we go out to the left and right, both arms are going to be going up. And it's not going to be going straight up. It's going to be going up in the shape of a parabola. We're going to graph this in a second, but I want you to think about this for a second, okay? This is pretty heavy. Okay, so if this, and it's not super, super important, although it is what you're going to be, a lot about what you're going to be learning about next year in calculus. Can I get you guys to pay attention here? Don't write this down, okay? This is not important enough to write down. But I want you to think about the limit as x approaches, I'm going to do infinity of this function, which is, so I want you to focus on this right here. Don't write this down. Just think about it for a second. And I want the answer. The question I want you to answer is, why do I not include this when I'm talking about the end behavior? The end behavior happens when x heads towards infinity or positive infinity. What is going to happen to this fraction over here when x gets really, really, really big? Say x is like 1,000,000. Estimate, what would the decimal value be if I did negative 12 divided by 1,000,000 minus 1? It's going to be 0.00, there's going to be a few zeros in there probably, right? This is going to be awfully close to 0, isn't it? What if x gets even bigger than 1,000,000? What if it's 1,000,000,000,000? Is this fraction going to get bigger or smaller? It's going to get smaller and smaller and smaller. The bigger x gets, the closer to 0 this thing gets. So the limit, as this part heads to infinity is 0, so we don't need to include it. That's why we don't include it in this thing, because it's insignificant. As x gets really big, this thing turns out to be equal to 0. Okay. All right. Get out your graphing calculators. I want to graph the original function and the end behavior asymptote together on the same graph. I want you to see, for this one example anyways, what's going on with this thing and how these two things relate to each other. So we got x, so don't forget your parentheses around your top and bottom when you're graphing in your calculator. There's my original. There's my end behavior asymptote. This will be a little bit easier for those of you who have the color version, because you're going to see two different colors of this thing. This parabola here, that's our end behavior asymptote. That's not part of our actual function. That's the thing that's going to allow us to predict what our function is going to do at the far left and right edges. Do you guys have that graph on your screen that looks like that? Is anybody having any issues right now? It's probably a negative and a minus, or you forgot parentheses. Are we good? Does anybody need a minute? All right, hit the window button. I just want you to change one thing for me. Change your Y max to 50. We're going to zoom out on this thing a little bit. There's my original function. And here comes my end behavior asymptote. I want you to focus on the outside edges of the graph, not what's going on in the middle here, but on the outside edge. Can you see that those two functions are really close to each other? If I were to zoom out further, we would find that these functions would be so close to each other they'd be almost indistinguishable. There would just be this little tiny glitch in the middle where one of them didn't match the other one, is what it would look like. One more thing, look at your table with me. Hit second graph to look at your table. And scroll down so you can see 0, or up, just get to where you can see x value of 0. Notice that the x and the y values for our y1, which is our actual function, and y2, which is our end behavior asymptote, now they don't really correspond to each other very well here. The numbers are way off. What I want you to do now then is start scrolling down, and as you scroll down, keep your eye just on y1 and y2. And what you're going to notice is that those numbers, they're both changing, but they're starting to get a lot closer to each other than they were in the center. And if I keep scrolling, eventually I'm going to find that those numbers are awfully, awfully close to one another. Like I'm starting to get into the magnitude of, like, the y values are close to 2,000 here, and they're only about 0.3 apart from each other. That's a very small deviation from each other. If we were to continue scrolling down forever and ever and ever, eventually the calculator would get to the point where it would be giving you the exact same two numbers. Because when it rounds it off, they're going to be rounded to the exact same two numbers. Now, do they ever match up exactly? No, but they get closer and closer and closer. So knowing what this looks like is helpful to us if we're dealing with a real world situation where what's going on in the center isn't important to us. If we want to know what's going on way out here, this graph basically boils down to this. Okay? All right. We are on last phase. We're going to skip this and come back. You're going to need your own notebook paper for this last problem. I'm just going to make a note here that we did this in our own notes. Last two problems here. we're doing pretty well on time. You guys are doing great. Oh, I did it again. As you're writing this down, leave a little bit of space above it. Leave a little bit of space above it. So the instructions say to analyze and sketch. So analyze means all that fun stuff that we learned in chapter 1. X-intercepts, Y-intercepts, domain and range, bounded, not bounded, continuous, not continuous. We'll look at symmetry, location of asymptotes, all that fun stuff. So for a lot of that, we're going to need a graph. So let's focus our attention on the graphing part. To build a good graph, we need to know where our intercepts and asymptotes are, and also look at our end behavior. So let's find those two things. So and this is the standard form of this function. We are going to factor it eventually. That's going to help us find intercepts and vertical asymptotes. But what can we do from the standard form? What's easy for us to do here? There's a couple things that are pretty easy to see in standard form. One of them is our end behavior asymptote. We usually look at that in standard form. So I call this my EB asymptote. Let's find our end behavior asymptote. Can we use one of our shortcuts for this one? We could. Because when we look at the degree, we've got the same degree top and bottom, so this is balanced. So it's just going to be y equals, is that y equals 0, or is that the one where we divide? We divide. 2 divided by 1 is 2. All right, that wasn't too hard. Let's start graphing this thing. As we come up with this stuff, we'll start building our graph. I'll tell you, you're going to need a, well, we'll see that in a second. So I'm going to leave a little space here. And here's our end behavior asymptote here. So I already know some important stuff about this graph. Like, what if I plugged 1 million in for x? What am I going to get out of it? Something pretty close to 2. So it's either going to be 1.9999999 something, or it's going to be 2.0000000 something. It's going to be really close, though. The other thing that's really easy to find when we're looking at our general form, standard form, is the y-intercept. Y-intercept is really easy to find for any function. It's just, what do we do to find the y-intercept? Guys, we got to know this. Plug 0 in for x. Yeah, f of 0 is the y-intercept. Always. Plug 0 in for x. If I plug 0, I'm going to get the top's going to be 0 plus 0 minus 12. The bottom's going to be 0 plus 0 plus 1. So I'm going to get negative 12 over 1. So my y-intercept is going to be 0, comma, negative 12. Make sure you write it as a point. Don't just write y-intercept equals negative 12. That's going to lose you points. Same thing here. I do not want you guys writing HA equals 2. Right? Y equals 2. Okay, 0, comma, negative 12. So yeah. I've already got this recorded. I'll put it up here. We're going to need some pretty negative values. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. All right. All right, those are the two big things that we know about the graph so far. I know the graph's going to go through that point, and I know that as we get really far out to the left and really far out to the right, the graph's going to be really close to that end behavior asymptote equal to 2. I'm drawing my graph right on top of it. It's going to be right above it or right below it, but it's going to be so close you won't be able to tell the difference. So just drawing it right on top. All right, the rest of our analysis, in order to graph this thing, we're going to need x-intercepts and vertical asymptotes, and that's going to come from the factored version of this. So it is time to use our factoring skills to create a factored version of this. I'm going to give you guys 1 minute to get the top and bottom of that thing factored, and then we're going to move on. Go ahead. Ready, start, go. Mm-hmm. Oh, I was, yep. And there's mistake number 18. Maybe 5. That's not right, is it? Thank you. I forgot to take my 2 out here. Why did I erase this? This was fine. So it's not 4 and 3, it's 3 and 2. Sound better? Plus 3 minus 2. There we go. Does that look better? Thank you, guys. Make sure you're doing a GCF first on the top. Okay, we're well past a minute there. So I'm going to move on. Go ahead and copy down what I've got here. Thank you guys for catching my mistake. When I did my GCF, I didn't take the 2 out of the 12, and so my factoring ended up being wrong. But we caught it. All right. Let's do some analysis here. So the numerator, these factors in the top, these are going to help us find what? X-intercepts. So our x-intercepts are going to come right from there. One of them is going to be negative 3 comma 0, and the other one is going to be 2 comma 0. And that's also going to tell us whether we're crossing or bouncing at those x-intercepts. And I think we're going to be crossing at both. So this is just like with polynomials. They're both singles, multiplicity 1, so we'll be crossing at both. This is a 3. What's the denominator tell us? What do these factors in the denominator tell us? Those gives our vertical asymptotes. We've got vertical asymptotes. Actually, there's only one. It's x equals. Remember, a vertical asymptote gets an equation. Not x not equals. Don't draw that line through that. We're not finding domain here. X equals negative 1. So let's draw our intercepts at negative 3 and at 2. And let's draw the vertical asymptote. There's only one. It's at x equals negative 1. And what does this square tell us about that vertical asymptote there? And they don't really bounce. Vertical asymptotes, they don't bounce. What kind of dance is it doing? Is it doing one of these? Or is it doing one of these? It's doing the thing where it's going the same. Now, I don't know if they're both going up or both going down, but the two arms are either both going to be going up or they're both going to be going down. Actually, I have a feeling they're both going down based off of where my points are right here. But it's going to be one of those because of that square. If it had been a first power, then they'd be going in opposite directions. So I think we're ready to graph this thing. You guys want to start on the left or the right? Or in the middle? Left. Let's start on the left. So we're at our end behavior here, and we need to come down, and we need to hit the x-axis here. And we said we were going to cross over, so let's cross over. And then as we move towards this asymptote, we either need to go up or down. Now, would it be possible for us to do a little U-turn and go back up here? Is that possible? No, why not? Because we don't have an x-intercept over here to allow us to cross over the x-axis. We can only cross or touch the x-axis where we have x-intercepts. We don't have one here. This is like a barrier. It's a wall. We can't cross it again until we get over here. So it must be going down, right? So as we head towards this asymptote, where our behavior is heading down towards negative infinity. And because that vertical asymptote was a multiplicity, an even multiplicity, we know we're going to be heading the same direction on the other side too. And that's good, because that sets us up to be able to get through our y-intercept here. And then as we move to the right, we're going to have to hit this y-intercept. And you guys said we were going to cross over there also. And that's good because that gets us on the right side of the x-axis to meet up with our end behavior over here. So there's our graph. If we wanted to be certain that that was correct, we could plug it into our calculator, but I'm going to say it's looking pretty good to me. So any questions up to here? All right, so end behavior asymptote, we look at the degrees. We didn't have to divide this time. Y-intercept, find it the same way you do for any other function. X-intercepts come from your numerator factors. Vertical asymptotes come from your denominator. And then in your textbook, it's going to ask you to analyze these functions. So you're going to sketch and analyze. So let's do that. I don't want to. Let's say the end behavior and the behavior around the asymptote. So you guys, if we skip over that for this one, we've already practiced that here. Are we okay to skip over that? I do need you to do that for the analysis in general. Okay. We'll skip that for right now. We've got our x-intercepts, our y-intercepts, our asymptotes. Can you guys practice finding the rest of this stuff for me? Domain, range. Continuous. That's a yes or a no. Boundedness. What else do we have on there? Symmetry, which leads us to odd or even. Trying to think what else. I put a little cheat sheet for you on Canvas. Local extrema. AKA turning points. So none of this is anything new to us. Go ahead and finish those off. I'll put my answers up here. For domain and range, I'm okay with using interval notation, or I'm okay with you just using, well, what I've got up there. I'm seeing some questioning faces, so that makes me think I might have a mistake here. Yeah, it should be a 2 there. Thank you. Jeez. This is not my day, guys. It can go up to 2. There it is. You know what's funny is the mistakes I made first period today are different from the ones that I'm making now. But I got those ones right, both. So, oh, jeez. Anyways, I'm operating at a B- level today. Sorry, guys. I'm glad you're here to help me catch my mistakes. Thank you. I appreciate it. I appreciate your grace, not being mean to me about it. Any others? Any other corrections? When we say symmetry, when we are doing analysis, we're specifically looking for symmetry about the y-axis or symmetry about the origin. Those are the two important ones. This might have symmetry about this vertical asymptote, although I don't think it does because this is 2 units away and this is 3 units away. But that's not really that important. All right, if we were going to talk about end behavior, we'd say the limit is as x approaches negative infinity of f of x is 2. Same thing on the right. And then if we wanted to do behavior around this asymptote, we'd have to do a limit as x approaches negative 1 from the left and from the right, and they would both be negative. Let's go on to the next one. Last one, unless there's any questions here. Last one, it's on the bottom of your packet there. Again, if you leave some space above, that'll be useful to us. F of x equals we are going to need to factor this one eventually. Do you want to do it now or do you want to wait for later? Just do it now? Okay. What does that top third degree polynomial make you think of in terms of factoring? Do you guys remember when we did a warm-up problem last week where we factored a third degree polynomial, something with 4 terms? You remember that factor by grouping thing? Okay, well, let me remind you. Factor by grouping. So we're going to factor this thing. It's going to take us a couple steps. When we do factor by grouping, what we do is we look at the first 2 terms and we pull out a GCF. What's the GCF for those first 2 terms? X squared, and what would be left over inside if we factored out an x squared just from those first 2 terms? X minus 1, right? What I'm hoping is that I can factor an x minus 1 out of the last 2 terms also. Is that possible? What would I need to factor out in front to get an x minus 1 out of these last 2 terms? Negative 1. So if I can do that, then I can factor this thing into x squared minus 1 times x minus 1. it's the GCF becomes one of your factors, and then your common factor x minus 1 is your other one. Oh, and that factors even further, doesn't it? What is x squared minus 1? That's x plus 1, and that's x minus 1. So my final factored form for this would have, oh, thank you. What do we got? We got an x plus 1 and a couple x minus 1s. This is why I was pushing the factoring practice so much at the beginning of the year, because this is where it's going to come into play. All right, how about that denominator? Can you guys factor that pretty quickly? Yes, that's x plus 2, x minus 2. It's a difference of squares. Okay, so we got it factored. Oh, yep, that's it. All right, where shall we start? Want to start with intercepts or asymptotes? Intercepts? X or y first? Y-intercepts? All right, let's do a y-intercepts. F of 0. What's f of 0 for this? This would probably be easiest to do in this version. Well, we'd end up with a 1 on the top and a negative 4 on the bottom, so I'm thinking negative 1 over 4. Start graphing this thing. Negative 1 over 4 here-ish. How about x-intercepts? Those are going to come from our numerator. That x plus 1 is going to give us negative 1 comma 0, and that's a cross or bounce. That'll be a cross. And this one's a double. It's going to be 1 comma 0, so we should be bouncing there. Denominator gives us vertical asymptotes. X equals negative 2 and x equals 2. What are we missing here? End behavior asymptote? We're going to have to do that, yeah. End behavior asymptote. Can we use a shortcut for this one? No, it's not bottom heavy, it's not balanced, so we got to divide. We're going to have to do long division here. Now, the good news is when you do this division, you don't have to carry it all the way out to the end. Can you guys stop for a moment wherever you are? Look at this division here and tell me, what degree do you expect to get for your quotient when you divide this? You're dividing a third degree divided by a second degree. You're going to get what? You're going to get a first degree. So it's going to be something x plus some number, right? Once I know what that coefficient and that number that's being added or subtracted, I'm going to stop. I don't need to know the remainder. We throw out the remainder anyways when we find the end behavior asymptote. It's just the quotient part. So I'm going to start my division, but I'm not going to carry it all the way out to the end. We only really need to go about halfway with it. So here we go. So let's divide here. I'm going to do x squared plus 0x minus 4 into x to the third minus x squared minus x plus 1 We'll stick some 1s in here. Unfortunately, we can't get away with synthetic division this time around. That's where I'm stopping. Yeah. Did I make a mistake there? Something doesn't feel right there. It doesn't. That's where it is. Thank you. I knew something didn't seem right there. Okay, so that's not a +3, is it? Something felt off, and it was. Thank you. Uh-oh. We're out. This should say x minus 1. This goes into this -1 times. Okay. That would have made sense. This doesn't go into 3 because it's x squared. Okay. X minus 1, and then that's where I'm going to stop. Does that look better? Okay. X minus 1. So my end behavior asymptote is y equals x minus 1. And then we'll graph that. So that's a line with a slope of 1, crosses at -1. And I think we got enough to graph this thing. Are we seeing any other mistakes there? Again, thank you guys for helping me out today. Say again. Yeah, I stopped at that point because the only other thing I'm gonna get out of this is a remainder, right? And I don't need to know the remainder. So I didn't complete the division. I got the piece out of it that I needed. All right, let's graph it. We know that at the ends of our graph is going to be indistinguishable from this end behavior asymptote. So I can just go ahead and draw the graph right on top of it. Even though it's not going to be right on top of it, it's going to be so close that we can't tell the difference. And then I'll start at either the left or the right. You guys have a preference? Or do you want to start in the middle? The left? So let's start at the left. Okay. So here's what I see as I move from the left. I see either we're going to have to curve up towards positive infinity, or we're going to have to curve down towards negative infinity as we approach that asymptote. Which one is the correct way? Down. How do you know that we can't curve up towards positive infinity? There is no x-intercept that would allow us to cross in between there, right? Remember, this is a wall. This is a wall, and the only way through this wall are these x-intercepts. So we must be curving down towards negative infinity. That's on that side of this vertical asymptote. What's going to happen on the other side? This was a single, wasn't it? So it's doing one of these dances. If it's going down on one side, which way is it going on the other side? It must be going up on the other side. So if it's going down on the left, it must be going up on the right of that asymptote. And then we're going to move towards our x-intercept here. That's the next feature I see to the right. And we said it was going to cross at that one. That's good. That gets me down to where I can hit my y-intercept down here. Okay. And then we move over to this x-intercept, and what are we going to do with this one? We said we're going to bounce. Boing, bounces off. And after it bounces off, is it going to continue downwards or curve around and come back up? Is there a gate in the wall where I can come back up? There's no x-intercept there, right? So it's going to have to go down. And if it's going down on that side of the vertical asymptote, then it must be going up on the other side. And then I just need to get it to meet back up with my end behavior asymptote, which is good. Yeah, I'm already on that side. It should look something like that. I got a question for you. Yes, well, let me answer yours first, though. Sure. Okay, yes. So, and I'm super glad you asked this question. Thank you, thank you, thank you. So there was a key phrase that you said just a moment ago that phrase is what's causing your confusion, okay? You said the part in the middle, okay? I don't want you looking at this and seeing this part, and this part. We've got to just block that out of our mindset, okay? This is all one function. It's all one function. If you want to split it up and look at some individual pieces of it, I would encourage you to look at what's happening with this asymptote and what's happening with this asymptote. Ignore everything else that's going on. So when I look at this asymptote, see how they're both singles here. They both came from multiplicity 1. When I look at this asymptote, are you seeing doing the single asymptote dance? One arm up, one arm down. So we're good there. And when I look at this asymptote, same thing. One arm up, one down. We don't want to start looking at this and saying that's an arm up and an arm down, because that's not an asymptote. That's two different asymptotes and an arm from each, right? So just focus on that asymptote and what's immediately to the left and right. Does that answer your question? It was a really, really important question. Thank you for asking that. Again, it's very tempting to look at this and see we got the part in the middle, the part on the left, and the part on the right. I encourage you to try and not think about these as separate parts. Think about it as one graph and focus your attention on the asymptotes. Maybe keep a couple note cards tucked into your notebook that you can use to kind of separate that out and make that easier to see. Yes? Another great question. Why is it able to cross the end behavior asymptote? There are no rules, and there never have been any rules about graphs crossing an end behavior asymptote. They can totally do it. I'll tell you, if they do, it's going to happen somewhere in the air quotes middle of the graph. Okay, so it's going to happen in the portion of the graph where it doesn't actually follow along with that. And it can cross it as many times as it wants. Now, as we leave the middle of the graph and we head out towards the far ends, then we shouldn't see it crossing back and forth. Actually, that's not even 100% of the time true either. We'll see that with some of the oscillating functions, the periodic functions that we'll deal with later. For rational functions, it won't. This one happens to be above that, and it's always going to be above it. It's never going to cross it over here. It's just going to get closer and closer to it. But in between, it can. Now, the hard and fast rule is that it can never cross a vertical asymptote. Okay, that can't happen because those things aren't part of the domain, right? Those aren't even valid x values that we can put inside of the function. So my question back to you, just to make sure you understand, is it okay for a graph to cross a horizontal or end behavior asymptote? Yes, as long as it's doing it in the center of the graph, okay? And actually it can do it anywhere it wants to. Another great question. Thank you, guys. What other questions do you guys have? We're not going to go through and do the whole analysis piece for this because I feel like you guys have done that a million times and you'll get the chance to do it in your assignments too. So, all right, let's call it a wrap. I don't have time to check your assignments today, but